Smart materials are transforming our world. By understanding their innate properties, we can design objects that are greater than the sum of their parts. We can create products that perform and function better while using fewer resources. In a world increasingly impacted by environmental degradation and over-extraction of critical resources, designing smart is the only way forward. When it comes to smart textiles, researchers are exploring fantastical ideas such as
fabrics that can self-tailor, change shape and color, or even respond to the surrounding environment, both physical and digital. In fact, there seems to be an increasing number of designers
thinking about interdisciplinary fashion,
like Iris van Herpen, Sohail, Hussein Chalayan, and Rei Kawakubo. Intersectionality as a guiding principle for greater design, and my inspiration for a project that looks at combining my education in architecture, research in active matter, and experience in fashion design. The Anthropocene poses designers with urgent and significant challenges. I propose that no single field of study can hope to respond alone. Through unique and creative collaborations, we can start to achieve solutions. In this project, you will see how fashion design can offer insights on a more gentle use of materials. It will show how, through smart clothing, we are woven into a more digital experience.
In this project, I explore the electrostatic properties of materials and their value to fashion design. You have probably already experienced this property in the textiles around you.
Imagine if you were to shuffle your feet across the carpet. Electrons would transfer from your skin onto the acrylic fibers, causing a buildup of positive charge. Upon meeting a conductive surface, the electricity discharges in an experience commonly known as a static shock. It turns out that some insulative materials can store a significant amount of charge before reaching saturation and ultimately discharging. When you see this happen, you are actually seeing the discharge of thousands of volts of electricity leaping from your finger to the conductive surface. The production of static electricity is a phenomenon more scientifically known as the triboelectric effect. Studies into this phenomenon have mapped out the relative charge affinities of various insulative materials into a list known as the triboelectric series. From this list, we can see which materials are most likely to gain electrons and which are most likely to lose them when they come into contact with one another. Interestingly, many of these insulative materials are also recyclable. What's exciting about this phenomenon is that it can be used to effectively convert mechanical energy into electrical power in a process known as triboelectrification. First invented in 2012, the triboelectric nanogenerator, abbreviated TENG or TANG, is a device that makes use of the static electrical capacity of insulative materials to produce useful, low-voltage energy. Following this research, I was able to uncover an intersection at which fashion, architecture, and active matter can collide. In a garment, triboelectrification gives the user additional capabilities, making it more valuable and less likely to be thrown away. It makes use of materials that tend to be discarded far before the end of their usable lifespan. It offers an alternative method of energy production, one that is autonomous and clean. There are so many potential applications for this technology that could dynamically change the way people engage with the built environment. Because our clothes become more like houses, our physical activity gives us power. It has the potential to alter the ways we configure with the virtual realm as our smart clothing deepens our connections with our broadening digital existences. The global digitization trends are accelerating the impact and influence of technology in our lives. We are engaging differently with the world around us because of it. Design and architecture are no exception. Thinking on the implications of rapid technological development, I experimented with sketching initial garment designs in a virtual reality program called Tilt Brush. As a design tool, VR allowed me to explore the volumes, colors, and even textures of the designs I was recording on paper, and proportions became much clearer. Thanks to this application, I could quickly trace over a dress stand without fabric or scissors and make new and informed assessments of the design before committing to an expensive mock-up. In each of the designs you see here, I attempted a different strategy for how triboelectric components could be incorporated into a finished garment. I propose both plastic triboelectric fringe embellishment components and fabric ones. I look at how momentum from the body's movements could maximize separation between the fringe components and maximize voltage production. I also consider how fabrics are naturally engaged in torsion and abrasion while worn, optimizing placement of triboelectric components in those areas. Pleats, folds, embellishments, and ruffles can all play a role in an effective triboelectric nanogeneration strategy. In this new area of research, There are many techniques and applications to be explored to understand how tangs can be best optimized to provide stable and usable electricity to the wearer. Exploring the fabrication of a tang proved to be as challenging as it was ambitious. I started by exploring the production of plastic embellishments recycled out of wasted materials. To do this, I built a plastic injector and designed my own injection molds. Several issues quickly arose in attempting this. First, it became clear that a high degree of precision was needed in sizing the melting chamber to maintain pressure on the melted material and force it into the mold. Second, the design of an injection mold is far more complex than I had anticipated. They must be efficient so that the hot plastic does not have a chance to cool and jam within the channels of the mold. This has led me to reconsider the injection mold process. I moved instead to using fabric swatches to test whether I could produce a non-insignificant voltage and move it through a circuit running an application. My swatch studies were very successful, demonstrating several potential options that could produce voltages high enough to power LEDs. Based on this outcome, I selected an aramid-cotton combination that would inform my final design. Additionally, I felt that the design's performance could be aided if the surface area of the triboelectric components were increased and placed on the garment so they would be forced to interface. To test this, I developed a bias strip lined with conductive fabric that would be appliqued to portions of the garment in alternating sequence. Tests confirmed that this method produced significantly less voltage, but a more stable output. I therefore decided to proceed with this technique. The final design is a tailored bodysuit designed to fit close to the body, so that movements and torsions most strongly affect the garment. Finally, an array of LEDs was included in the garment to provide a visual confirmation of its functioning. The world of design is changing as it responds to the challenges of the Anthropocene. This project proposes a hybridization of fashion, architecture, and active matter, which demonstrates a unique possibility of habitation and a more gentle and intentional use of materials.